Let's now talk about how we can implement the stack ADT in Java. And I would like to start by pointing out we are going to use an interface construct in Java rather than maybe having different classes for the stack. So there is a really important software design reason behind that. So we really want to exploit or take advantage of the polymorphism and dynamic binding, which you learned about in the earlier advanced OOP course, which I will try to review a little bit when I get there. But let's now take a look at the Java interface. And remember, in the very beginning of lecture number 3, I mentioned that interface should be some background study. You should really do. If you don't feel confident about what you learned about interface earlier, you should really go to the resources I pointed out to you. If you got any trouble reviewing that, reach out to me, please. All right, let's now talk about interface. And in Java interface, the only thing you declare will be the method headers. You want to specify what kind of method it is. It is either accessor or mutator. And you don't really declare any attributes. You don't really supply any implementations to the methods. So that's Java interface. It's a very nice and clean layout for what you can expect as a user, as a client. So what about the stack? All the operation that we spoke about earlier in the illustration, they should be declared in the interface. So we got size, we got it's empty, we got the top, we got push, and we also got pop, right? You can see terminology is exactly consistent with how we learned before. And now you shouldn't really feel strange about the generic parameter over here. I'm going to assume you're actually feeling comfortable about generic parameter. If you got any trouble understanding it, you should really reach out to me, okay? And so the stack ADT declared as an interface in Java allows alternative implementations to conform to its method headers, meaning that we can have the following architecture, right? So we can have maybe one class called the array stack, and in this particular class we're going to implement the stack, the last in first out, the LIFO stack, using an array, a single array. We can have another independent class which is also going to implement a stack ADT. In that case, we're going to use a singly linked list, let's say. However, we don't really want these two classes to be completely unrelated to each other, because we want the user to actually really have the freedom to say at the runtime, I can switch between the array implementation to the linked list implementation, or vice versa. They should be able to switch from one to the other quite freely and smoothly. And the way to really and what can really allow this to happen is the polymorphism and dynamic binding idea that we're gonna see. So that's why at the top we're going to declare this stack interface, which we just saw, right? Everything's gonna be generic, right? You can see the generic parameter E, and also E over here. And both classes are going to implement the stack interface, right? And let me now just talk about this diagram here. Nothing I want to add. What I want to really point out to you is the reason that we really want to have this particular architecture over here, interface, and two implementing classes over here. As we'll see, what's really important for you to understand about this particular architecture will be polymorphism and dynamic binding. Okay, polymorphism. And this is something you will see in the background study as well. Dynamic binding. Specifically, since the stack is actually declared as an interface, so stack interface should be used as a static type. And either this class or this class over here, they can be the alternative or candidates dynamic types at the runtime. Candidates dynamic type, meaning that you can actually switch from one to another. And of course, if you really want to determine which one it is currently, you can use the instance of check if you want. All right, that's all I want to say about this architecture. You should really see exactly how this happened. Let me point out to you where you can find it. And I can only just highlight about the important bits about the implementation, which I will do for the array and for the linked list. But for the remaining details, I need to rely on you to really explore yourself. So go to the project I made available to you. It's called the example generic stacks over here. Under SLL, so this is some partial implementation for a singly linked list, which we spoke about in lecture number 2. And you can see on the model, we actually got this stack interface over here, right? Exactly consistent with what you saw in the lecture. And also we got one implementation. You can see array stack, which implements the stack. So that's something we'll go over as well in detail. And the way we implement another ADT, like a queue, will be somehow similar. So I don't need to spend as much time. I'll spend a little bit more time on going over the array implementation for the stack. And we got another alternative implementation called the link stack. And this one here is actually going to use a singly linked list as a private attributes, right? You can see link stack also implements the stack interface, right? That's exactly the architecture that we saw over here. It's really important to keep this architecture in mind. Every time we introduce a new ADT, most likely you can simply declare the ADT itself as an interface on the top. And then there might be different ways for you to implement that particular ADT, at least by array, by a singly linked list, and also by some doubly linked list. But for the case of queue, we're going to show you another interesting manipulation for the array called a circular array. That's something we'll see later, right? Just keep you motivated. Well, it will come. Okay. All right, so that's about the source code you can explore, and there's another class over here called stack utilities. So once we get to the applications of using stack, you will also refer you to the code over here. But for now, you're okay. And under the tests package, you can see we also got the test stacks over here. So all the source code we talked about in the slides, you can also find them over here. As usual, my advice would be try to maybe explore the source code yourself by using the debugger and also breakpoint, right? It's always a good thing for you to really get familiar with. Right, let me go back to the slides. Right, let's now talk about implementation number 1, which is use a single array to really implement the stack. Let me now walk you over the logic for the code block by block, and then we'll talk about the runtime maybe on my iPad. That'll be the plan. Let's now talk about it. So we got the array stack, which is itself generic, with a generic parameter E, and also implement stack E. You can think about whatever E this will be instantiated, is going to instantiate this as well, right? Let me just talk about this specifically, okay? You can think about the E over here is a generic parameter, and once this is instantiated, it will be used to also instantiate this particular E over here, right? So these two E's actually are related to each other. So for example, let's say for me as a client or as a caller, if I declare array stack over here, if I say array stack, let's say string, so this declaration over here will instantiate the generic parameter E for the stack. More precisely, it's also going to instantiate the stack of string. Right? It's very important for you to realize by declaring this type, at the same time, it's also going to set this aside by the compiler, right? Whenever you instantiate this E over here, it's also going to instantiate this E accordingly. Of course, every other E in the scope of the class will be instantiated as well accordingly, for example, right? I'm just highlighting some examples over here. Right, let me go back. And let's now talk about the different attributes or methods. The first one here is not really an attribute. It's simply a constant. Remember the final keyword in Java. So we are setting some maximum capacity for the stack. And the 1000 over here, I simply chose a number arbitrarily. So you can feel free to choose any upper bound you kind of prefer. But the most important thing is, so that means with this particular finite amount, eventually, let's say if I already got this many items in my stack, why is it 1000? I definitely cannot go above this particular limits. That means if I try to push more than 1000 elements into my stack, I'm not going to have any resizing of the array. I'm actually going to have trigger some precondition violation. So it is so important for you to realize this, right? So we're going to see eventually to do some comparison, like this fixed size array implementation versus the so-called dynamic array implementation, which we'll see at the end of this particular lecture. We'll see that. I just want you to keep in mind. So that'll be the distinction we have to make. Right, so we got some private array over here, and its type will be generic depending on what E will be instantiated over here. And also we got a pointer, like a counter over here. So this is an integer counter. You can think about T is going to store the index about the top of the stack. And for this particular implementation, I want you to answer yourself this question. We got two possible cases over here. Either we can treat the very beginning of the array as the top of the stack, or we can treat the very end of the array as the top of the stack. Or more precisely, let's say if you got an array of size 10, you got 5 elements in the array. In that case, should the first element treat it as the top, or should the 5th element, the last item over there, to be treated as the top? We got actually two choices over here. I want you to watch out as I go over the code. Tell me which one, which case it is. Are we treating the beginning of the array as the top, or the other way? And we got a constructor over here. And this one thing I want you to realize over here, this is some unfortunate compromise we have to make when we want to instantiate some generic array in Java. Okay, let me highlight it for you. You can see here, in order to really instantiate this array over here, which is generic over here, in order to do that, what we have to do is we have to create an object array, and then we have to do a cast into E, right? So that's what you gotta write. So, right, so you're gonna say objects array. Of course, you're gonna give some size over here, and then you cannot really assign this directly to data, because data is supposed to be of type E, depending on what E has been instantiated. So that's why you have to cast it. So E array over here, right? So that's what you will see on the right hand side of this part of the code, right? This is something that's only specific to Java. I'm not too sure about other language which also supports generic, but it's just something you have to do if you want to write valid Java code, right? So this is actually what you have to write in. Very briefly speaking, when Java was first released for its very initial version, it was not designed with generics being supported. Java generics was only supported actually when I was an undergraduate student, so that was many years ago. So I'm talking about the beginning of year 2000. So around that time, when Java was first introducing the generics into its language, somehow the compiler wouldn't actually support the generics in the perfect way. So that's why you have to do such compromise to really create an object array to make the compiler happy, and then cast it. That's something you got to do. Also for the runtime to actually work well. For other language which support generics, if they actually release their very first version with the generic support already, you may not need to actually write such weird code. But for Java, we have to. Okay, let's go back. Right, so the size method over here is simply return t plus 1. Think how this is going to work. T is assigned to be -1. Why? Remember, T is supposed to denote the index of the top elements. Initially, the stack is simply empty. Conceptually, if the stack is empty, should the top be defined? No, it should be undefined. So that means it's -1. And so if I say -1 plus 1 is going to be 0. So the size is going to be 0. And later on, if the top is referring to, for example, index 2, in that case, that means we got 3 elements so far: index 0, index 1, index 2, and etc. Right? That's why t plus 1. I'm going to trace the code a little bit briefly with you a little bit later. And it's empty. We just check to see whether or not t is actually -1. And we're going to say top. So where is the top? So this is the critical method for you to decide, for you to answer my earlier question. Like for this implementation strategy over here, which side of the array is the top of the stack, the beginning or the end? So this tells you the answer. So whichever value t is going to refer to the top. So we are really talking about around not really the beginning side of the array. It should be whatever the last elements it is in the array from the left, right? That's something I'll visualize for you. And of course, you cannot actually try to inquire about the top elements of the stack, in which case it would be a precondition violation. But if you look at the source code, let me show to you. So if you go to the source code, let's go to the array stack For example, you will see that in the case of top, if it is empty, so the way I implement precondition violation is by throwing some illegal argument exception, right? So precondition violation is something conceptual you must know. And to really implement it, you can just throw maybe some kind of exception. Either you can throw illegal argument exception, or you can simply create an exception by yourself. Either way, you know how to create the exception classes yourself from the earlier course. If you don't know, let me know. Alrighty. And we got also the push operation. And this one is also very important, right? You can see here we're saying that if the current size is already reaches the maximum capacity that we set over here, can be arbitrary number. In that case, it will be precondition violation. Otherwise, we can simply increment the index for the top, and then we're going to assign the new top, the new top to be the element E, right? Conceptually it makes sense, but we're going to trace the code together. But you might already get convinced about this implementation. And finally, we actually got a pop operation over here, pop method. So we not only that we're going to remove the current top. You can see this part over here is where we actually remove the current top just by assigning the element in the current the old top index to be null, and then we're gonna decrement the index over here, right? In that case, we also need to return the old top. So you can see result is assigned to data at index t. So this is the old top. So we want to make sure not only that you remove the old top, you also return it, right? That's something we visualized earlier as well. Right. So that's the implementation of a stack using a single array, right, with a fixed size. Let me talk about the running time. Why don't we talk about it, right? Let's go one by one. What about the first one over here? Let me just highlight each one of them. What about the size method over here? Well, the size method here is simply just return, right? So it should be big O of 1. That one's obvious. What about is empty? Similarly, it's also returning some relational expression. That's also big O of 1. What about getting the top? Well, getting the top over here, well, we got two cases. Either you throw some exception, or it simply returns an array indexing expression. So it should be also constant. Also constant. Over here. Right? You know what? Let me just put the running time maybe right beside the code. I think that will be more organized. Let me do that. Okay, you can see the size method is actually big O of 1. And for the is empty is also big O of 1. For the top is also big O of 1. Either case, right? What about the push? The push over here, also we got two cases. Either the current the maximum capacity has been reached, in which case we trigger the precondition violation, which is over here. Or we actually going to push the element to the top index. Right? Either case is going to be, you can see it does not require any loops. Right? It's simply some simple arithmetic and also array indexing. So it's also going to be constant. So far, you can see it's a very efficient implementation for the stack. Finally, what about the pop operation? Right? You can see none of the cases over here involves a loop. Right? You can see checking Boolean condition, throw some exception, and also just primitive operation as far as we can see. Right? It's also big O of 1. Right? So now you can see in summary, we got constant time operation throughout over here. So this is a very efficient implementation for the stack. Okay, very efficient. Efficient implementation of stack. However, what's the biggest drawback? As far as you can see, it's not really something that's wrong, but it's a drawback, it's like a limitation. The limitation really is over here. We don't allow the size of the stack to be extended. That's the biggest limitation. Okay, so this is the limitation for the stack. Okay, let me just write better. It's a fixed size. Whatever number you set it to be, you better make sure it's never reached. Otherwise, you just have no way to really grow the stack until you actually pop something off. We can actually resolve this by either using a linked list, in which case you don't really have the maximum capacity, right? Because it's a dynamic structure. Or we can use something that's called dynamic array rather than fixed size array. That's something we'll see at the end of this lecture, right? So just understand about nothing wrong with this implementation because it's very, very efficient. However, the limitation is you just cannot really change the size of the stack. It's already fixed over here. Right? Running time, I spoke about each one of them. It's all constant throughout. Okay, so this is one exercise for you to really do. Okay, if you want to discuss the answer, you can reach out to me. Okay, so the version of the implementation treats the end of the array, the top index, as the top of the stack. Would the running times of the operation change, either improve or get worse, if we treated the beginning of the array as the top of the stack? Meaning that the top index should for the stack should always be 0. Right? So what we want to do instead is to say, if this is your array, right? If this is your array, and this is your data array for the stack, and we somehow want to make, we want to treat the beginning of the array over here to be the top of the stack. If you want to support this kind of interpretation, would it be expensive or efficient? Right? So this, our goal is to treat this first item as the top of the stack. In order to really support this particular interpretation, what's the cost? Right? That's something I want you to think about as the exercise. Okay. And another question. What if the present capacity turns out to be insufficient, right? That's exactly this limitation I'm talking about over here, right? If the maximum capacity has reached, what's going to happen? Well, in that case, we get precondition violation. But the good thing is the running time is very low. It's only a constant amount of time to really throw some exception, like a returning something. So that'll be illegal argument exception, which will take a big of one time to respond. At the end of this lecture, we're going to learn about another alternative using the array. It's called dynamic array by introducing the ability for the array to resize itself. That's something we'll see.